Alright, we're going to be doing question 47 and 49. It has to deal with Gibbs energy. Alright, for question number 47. We're given this generic formula. 2A in a gas form plus 3B, also in a gas form, has a forward and backwards reaction with 2C and 4D. We are given the molar concentrations of all four variables. A is 1.8 times 10 to the negative 2 molars. B is 3.4 times 10 to the negative 3 molars. C is 5.6 times 10 to the negative 1 molars. And D is 2.8 times 10 to the negative 4 molars. We are given the temperature, which is 25 degrees Celsius, which is equal to 298 degrees in Kelvin. We are given the K equilibrium, which is equal to 4.42 times 10 to the negative 9. For this question, it asks us to find the change in Gibbs energy under standard conditions. We are also looking for the Q constant. Or I guess it's not really a Q constant, but what it is both of the reactants multiplied together divided by, both of the products multiplied together divided by the reactants. So it would be C times D over B times A, and that will give you Q. I just realized this is out of focus a little bit. Almost there. Alright, that seems a little better. And once we have the Q, we can calculate the change in Gibbs energy, but under non-standard conditions. Alright. So calculating it under standard conditions, which is this notation. It's delta G with the circle thing. I'm not really sure what it's called, but that's irrelevant at the moment. And the formula is negative R, which is a constant, T, which is temperature, the natural log of the K equilibrium. So altogether, to calculate it under standard conditions, you're given all three variables, and you just plug it in, and the value you get is the Gibbs energy under standard conditions. And the standard conditions are usually set by that IUPAC. And so we have negative 8.3145 joules per mole, which is R, times 298, which comes from right here. We're given that is 25 degrees Celsius, plus you add 273 to it to convert it to Kelvin, and the K equilibrium we've already given, which is 4.42 times 10 to the negative 9. So if you plug that into your calculator, you get the Gibbs energy under standard conditions is equal to negative 1.095 times 10 to the negative 5 joules per mole. And this is a chemistry-driven process, and it's very low energy. From the value of the Gibbs energy, we can tell that it's an exothermic reaction. Because it's negative, that means energy is released, which also means that it is a spontaneous reaction, which means that this is more likely to happen in a chemical setting. Alright, so that was part 1 of what the equation asked, or the question asked, for number 47. And alright, for number 2, we're going to be figuring out what Q equals. And like I said, it was the products divided by the reactants. And so we have 5.6 times 10 to the negative 1 molars times 2.8 times 10 to the negative 4 molars all over 1 times 8 times 10 to the negative 2 molars times 3.4 times 10 to the negative 3 molars. And just to put this in perspective, 5.6, this is the C species, this is the D species, and the A species, and B species. And just to reiterate, these are the molar concentrations, and it's the products divided by the reactants. And if you plug this into your calculator, you get a Q constant that's equal to 2.562. And once you have the Q, you can go ahead and calculate the Gibbs energy, and this is going to be under non-standard conditions. So we're going to take the change in Gibbs energy under standard conditions, which we already have. We're going to add that to the R constant times T, which is temperature, times the natural log of Q, and Q we just figured out. So once you find Q and you have the change in Gibbs energy, or Gibbs energy under standard conditions, you can calculate the Gibbs energy under non-standard conditions. So we have, let's see, can you still see this? Alright, that's better. So we have triangle G, which is equal to negative 1.095 times 10 to the negative 5 joules per mole times the R constant. Or no, add that, and then we have the R constant, negative 8.3145 joules per mole times 298 times the natural log of Q, which is 2.562 natural log. And once you have that, you just plug that into your calculator, and you get negative 2,331.01 joules per mole. And this is also an exothermic reaction, since the Gibbs energy is negative. And like I said before, from this you can take away that it's a spontaneous reaction, and energy is released during this reaction, and it's quite a bit of energy, 2,331 joules per mole. And this is a chemistry and molarity driven process. And that is the end of question number 47. Alright, next we move on to question number 49. Alright, and we are given the following formula: magnesium is hydroxide, which is a solid, plus 2 hydronium ions. In a reversible reaction, magnesium 2 plus 2H2O, and for this equation, we're given this formula. We're given that it's at 298 degrees Kelvin. We're given the change in Gibbs energy under standard condition, which is negative 95.5 kilojoules per mole, which is very high energy. And we're given the Q, which is equal to 2.389 times 10 to negative 4. And we are solving for Gibbs energy under non-standard conditions. And so Gibbs energy under non-standard condition is helpful when you have a different temperature, since that variable is in the equation. We are given the Q constant, so we don't need to know what the molarities are because it's given to us. There you go, you can see this now. Okay. I didn't realize focusing was going to be this hard on the camera. However, back to the equation. To solve for the change in Gibbs energy under non-standard conditions, you basically plug this into the formula, and that's about it. Alright, since this is given in kilojoules per mole, which is negative 95.5 kilojoules per mole, you basically multiply that by 1,000 joules over 1 kilojoule, and you shall get 95,000 joules per mole. That's 95,500 actually. Alright, so once we have that, you basically just plug it in, 95,500 joules per mole, plus the R constant, times 298, which is the temperature, times the natural log of the Q, and that was given 2.389 times 10 to negative 4. And that's the basic formula. You plug it all together and you get Gibbs energy under non-standard conditions of 116,016.875 joules per mole. So you have 116,016.875 joules per mole, which is extremely high energy. And this is also this is a spontaneous reaction. From this you can take away that's exothermic. and this is usually more likely to happen since no work needs to go into the system. And that concludes both of the questions.